Good night, everyone. Today we will have international talk. Good night, Professor Leszek. Thanks for your time. I will start. I will just start with Portuguese, and after I will switch back to English, ok?
Tudo bem.
Boa noite a todos. Nós vamos iniciar então a palestra do professor. Eu peço o nome, qual vocês participam ali no chat do YouTube, tá? Se vocês quiserem fazer perguntas, pode utilizar também o chat. E também, se quiser fazer, mesmo se quiser fazer em português, pode fazer, que daí traduz ali ao final ali da palestra do professor Leszek. Professor, eu said the YouTube chat, they can use the chat to make questions, and then people can make use the question to the audience. Okay. And Professor Leszek is professor at INRS of University of Quebec, Canada. He obtained the Master Engineer degree from Warsaw University of Technology and a PhD from the INRS Telecommunications Montreal. From 1998 to 2001, he held the position of assistant professor at the Department of Electrical Engineering, University of Chile. In 2009 and 2010, as an American research fellow, he was at CNRS L2S, GIF Survivant French. His research interests are in the areas of mathematical model, estimation, signal processing, and communication. He co-authored bit interleaved code modulation and analysis and design. And today, Professor presented the real-time reports. Thanks for your time.
All right. Thank you, Marcio. So, welcome everyone. For me, it's the first time to speak in such a virtual audience. I'm not used to that. Hope it's gonna be okay. And so I promised Marcio two things, I guess, or three. So first of all, I'm trying to speak slowly, so we can all follow what I'm talking about. And second of all, I promised to finish within 1 hour, right? So, and whatever happens, we finish before 8, right? So if I don't finish the slides, doesn't matter. I'm trying to be as concise as possible. And if anyone has questions during the presentation, by all means, please ask. Please, I don't know if it's raising the hand or putting some words in the chat, because for me it's better if nobody is lost, right? Because it's better to understand a couple of slides than not understand all of them, right? So, by all means, please. So, and it's also when you ask questions, also it's better for all the other people who listen, because sometimes it's a puzzle and we are filling in the empty spaces in what is not clear. So tonight's talk is about ranking, right? So the idea was to have a fun talk, right? There are some equations there, but it's mostly meant as an overview of some issues related to the ranking, and to make it more fun, it's about ranking in sport, right? So I know people here in Brazil, I mean, maybe it's a stereotype, but are fans of football or soccer, what we say. So there is some soccer results as well. If you are patient enough to stay to the end, I hope I will be able to get there. Right. I will just briefly go about what rating or ranking is about. So ranking fundamentals, and I will talk about what I call a power ranking. This will be an opportunity to talk about ordinal models, ordinal data models. And later on, I will talk about real-time power rating, right? So this is basically all the kind of focus and will allow us to introduce some Bayesian models and probabilistic modeling approaches will be shown. And I will explain how this leads to the new algorithm which can be developed in a quite flexible manner. And as I promised, there are some numerical examples from the sport world, including soccer, right? So I will conclude if I have time. Okay, so what I want to say, well, first of all, introduce the concept of ranking, and I will talk about the practitioners and theoreticians' perspectives on the ranking problem, right? Because usually people who work in the ranking are not statisticians, are not signal processing experts, are not computer science experts. Very often those are people who are fans of sport, right? And they just propose solutions for the ranking problem which somehow work, I would say. But how well, that's a different issue, right? And I will show some application in sport data. Okay, so that's the whole objective. So let's start with the overview, what it is. So let's suppose that we have the sport when there are m teams, right? M is a number of teams, and we index those teams with indices from 1 to m. This could be, of course, not only teams but players, like in different sports we have. But the context in which we are formulating this problem is that the games are played between two teams or two players, right? So those are one-on-one games, like soccer games. Team sports are usually like that, right? So we have one team playing against the other one. So it's slightly different of other sports when the players where we can have multiple players competing simultaneously, right? Like racing or sprints, 100 meters and so on. So here we are interested in games where two opponents face each other, and we have what we call a home team indexed with IT. It depends, of course, on the index of the game, which we say T. And we have an away team, which we index with JT. And we denote the outcome by the letter Y. Of course, index with T again. So what are the types of the games we will be interested in, or we will use throughout the presentation to talk about the problem? So the first, and maybe most likely the simplest case, we say that we have binary games. So the outcomes of those games, or results of those games, have only two possible values belong to set of two elements, right? So I call those H. So this is a home win. So that's why letter H, where the home team beats the away team, IT beats JT, right? And we have the A, where the other way, it's going other way around. The away team beats the home team, JT beats IT, right? So this is a simple case. And such a games, of course, in soccer, of course, we have slightly a different context. So we have ternary games when we have home win result, IT beats JT. We have a draw, right? So JT draws with IT. So there is, for example, in soccer, when both teams score the same number of goals, this is a draw. And away win. When JT beats IT, again the same result appears. And of course we can have other types of games, multi-level games, and then maybe instead of using letters, we can use simply the integer values. So we have L levels, index from 0 to L minus 1, and we say that result O, so this is, so I'm trying to use this, so this means that 1 is more important than 0, this means that 2 is more important than 1, etc. Right? So the most important result is L minus 1. Alright, so this is kind of definition of different types of games we might be interested in. And this kind of games, like those here, for example, so we could have volleyball, right? Volleyball games where you have 6 results, right? You can win by 3-0, you can win by 3-1 or 3-2, and you can lose in the same way. So 6 possible results. Here this is a soccer, right? And here, well, we can have, for example, tennis, right? Tennis game when there's always one winner. There's no draws. Okay, so what is the ranking? Ranking basically means that we have to order now the teams, right? So there's a team number 1, which is better than or precedes team index with M2 and team index with M. So basically we find the permutation of those indices we had here, right? They are permuted in the way to say which team is the best, so M1, and which is the worst, M sub capital M, right? So this is a simple idea and how to do it, right? So of course, well, I'm doing something probably for you which is obvious, right? So this is a conventional score point counting, right? So we attribute score points to the game result. In the binary game, we say, okay, if we have away win, we give the home team 0 points. If we have home win, we give the home team 1 point. Okay, that's, or some multiplicity of that, doesn't really matter. And we add the points at the end of the season, for example, right? So this is where we add points for the given team when it plays at home, and we add the complementary of those points if they play away, right? So if the team wins being away, so RT was 0, we give it 1 point. Right? Basically, it's the same as happens in almost the same as it happens in soccer, right? If we don't consider draws here, there are points attributed to the games, right? And then once you add those points, you sort them. So if one number of points of one team is greater than of the other, that means that one team is ranked higher than J, right? So this is so well rooted in what's in practice that sometimes it's confused with what the meaning of the ranking is actually, right? So because if we say, what does it mean that one team is better than the other? What does it really mean, right? So people say, okay, the team which has more points scored through this in this scoring, scored altogether or counted together, right? But this is a circular definition, right? Because you are the best if you have more points, and being the best means that you have more points. So there is no kind of root definition of what it really means, right? So that may be confusing, and there are some works on this issue as well, but I'm not talking about those issues. So there is something which we call power ranking. So we assign a real value to each of the team, which we call skills, power, abilities. Doesn't really matter what you call it, but this is a scalar value. we have to evaluate from the result. We sort the skills, and it gives us the idea what is who is better or who is ranked before who, right? So which team is ranked before which one. So that's kind of looks similar, but the models are basically simpler to understand in this power ranking. And then we have the interpretation of that, what it means of one team being better than the other, right? So that's the whole value of this power ranking approach. Well, that's what I'm trying to tell you about now. So, how to do it? All right, so this is the basic question. We would like to know how to rank the teams, right? So there is and what I call practitioner's perspective, and I will try to describe the algorithm, which is quite well known. It is called the ELO ranking algorithm, right? It's been around for a long time. It was devised around 60s to rank the chess players, right? So it's been in use for more than 60 years now, and it's adopted by the federal Federation, so it's a federation, chess federation, international and initially American chess federation. And how it works? So this is, we do the same, right? We assign score to the outcomes, and here I kind of emphasize that our outcomes, winning at home or winning away, or in the case of chess players, if the player who starts with white pawns wins, it's a home win, right? If the player who starts with the black pieces wins, then it's a away win. Those results, we just describe them in words. They don't have any numerical values, right? So those assigning of the points to ordinal outcomes may be confusing, but it's kind of inherited from what we saw before in the point counting system, right? So this is one thing. So we assigned those points to the home player or home team in this case, and to away team is assigned a complementary value. So it's exactly the same what we saw just before, right? And this is not enough because we still have to extract the skills of the teams from this approach, and we define something which is called expected score, right? So bear with me, this will become clear what it is immediately, but actually I call it practitioner perspective for a reason, because most often this ELO ranking algorithm I'm talking about here, it's actually defined very often this way, right? So people say, we have something which we call expected score, and that's it. So, and how is it defined? Well, it's a function G, capital G, of the difference between skills of the teams, of the home team and away team at time t, right? So if I have the difference of the skills, I pass them through the function, I have the expected score for the home team, and if I inverse the role, I take skills of the away team minus skills of the home team, I will have the expected score of the away team. So prime means away, and this bar means basically expected value, right? So here, of course, I would like to have this property that expected score for the home team is 1 minus expected score. Expected home of the away team is 1 minus expected score of the home team, right? And this function g of z should have this property, which we kind of axiomatically may define. So we say, larger the difference between the skills is, this z denotes the difference between skills, larger should be the expected score, right? So if the home team has skills which are much higher than the skills of the away team, this difference is very large. The expected score should be close to 1, and vice versa. If this difference is negative, so basically this one is positive, then the expected score should be 0, or the expected score for the away team should be 1. Right? So this is how it should behave. And in fact, since we have binary case and we assign the values here to each of the teams and we calculate expectation, mathematically speaking, basically this defines us the model. We say, now we can actually get rid of the notion of the score, and because actually if this is the expected value, so it means the probability that home team wins, so this is YT denotes the random variable being the result, given all the skills, it's essentially given by this function, right? But that's kind of in parentheses. Okay, so and then what we do? Okay, so we have the observed score of the game and observed after the game, of course, and we have the expected score before the game, right? So, and now we say, okay, if the score after the game is larger than the expected score, we would like to increase the skills of the home team, and vice versa. If the expected score for the away team is larger than the expected, if the observed result or score of the away team is larger, so this difference is positive, than the expected score, then we increase the skills of the home team, right? And K here is, I use this, maybe this is strange in this context, but people describing ELO algorithm are very much used to using K as this step with which this difference affects the skills, right? We can write everything like, so this is kind of positive feedback, right? If we exceed the expectations, we increase the skills. If we decrease it, if this is smaller than this, then skills will decrease, right? So kind of, it's a positive feedback. And that's it. That's how the algorithm is defined in practice. And we can write this in vector notation, right? So we have theta, which contains all the estimate of the skills, and we write it this way. So this R bar becomes this G, RT is the expected score, and actually all those with some manipulation we can be written this way, right? So that's very simple. This is based on, this is X, which we define like that. We have 1 at the position of the home player, minus 1 of the position of the, home team and away team, minus 1 at the position of the away team. So this is a vector which contains mostly zeros and just has 2 non-zero elements, which basically affect theta at those positions IT and JT where those elements are non-zero, right? So this is what's going on here. Why do I write it this way? Because there is a particular case, right? So if I replace G of Z by logistic function, right? So this is essentially well-known logistic function. So then I can write everything like that, right? And this is essentially the stochastic gradient approach for solving the logistic regression, right? So this is where we can link this algorithm, which was derived with any notion of logistic regression, to something which is now actually the bread and butter of machine learning scientists and people who work in machine learning, right? So I don't know if there are any questions I could take at this moment, if someone wants to ask before we move on.
Yes, no questions.
Everything, I suppose it's because everything is clear. Okay, so yeah, so what happens if we have more than 2 results? So this is where it's becoming slightly more interesting, right? Because we have, as we said, we have multi-level games, not only binary games. And for example, even in chess, right, we have where this ELO algorithm was deployed initially, we have 3 results. Sorry, we have away win, home win, and we have a draw. We still can draw in chess, right? So, and then what was done in this algorithm, basically they said, okay, I have the score which will be 0 as before, 1 as before, and now when there is a draw, I will have 0, 5. Okay, why not? We will go to it why it's so, and then since it's so easy, right, you can just add points somewhere here. Something similar can be done in 4-level games, and here it's example of FIFA ranking, international ranking, ranking of international soccer teams. So it's again 0 for the away team if winning, so the home team gets 0 points. It's 1 if it's a home team winning, it's 0.5 if it's a draw, and it's 0.75 if it's a draw and the home team wins in overtime, right? Okay, so basically you can do whatever you want here, right? It's kind of heuristic approach. You can add some other results, and it's all fine apparently. I mean, this is how the actual FIFA ranking is defined with respect to this RT, because it refers also to ELO, but it expands it by additional results here. Okay, so, and they say, okay, even if those results are defined the same, we still keep the same expected score, being the logistic function. However, in this case, we don't know how to define those probabilities, right? What is the probability of away team winning, or the home team winning, or the draw, or the overtime? It's undefined, right? Because here we essentially define only the expected score. Right? So that's kind of confusing a little bit for someone who wants to model those results or predict, let's say, the result. I'm not necessarily for betting, because that's also an interesting part, but for example, to know what are the chances of one team winning and the other losing. Okay, so here comes what I call theoretician's perspective, right? So theoretician doesn't derive the algorithm first, right? Because this is what the practitioner does in this ranking context. But the difference is that theoretician will always start with the model. I mean, at least in who is worth his own what they call grain of salt. This is what's called. Okay, so we start with what are the ordinals models we can do for the case. Let's say this simple one when we have 3 values, right? So there are already models known in the literature, and they are defined in a similar way. So, for example, you have some extension of the logistic function, right? So essentially, probability of winning at home when Z, which is, we remember, is the difference between the skills, when Z becomes very large, all this tends to 1. This is what we wanted, right? The probability of winning when the difference is large for the home team should be approaching 1. A similar probability of away team winning when this difference is large, so it's essentially the same as Z becomes very negative, so this goes to 0, right? And probability of draw is defined as a product of 2. So that's axiomatic definition, right? It's a multinomial logistic regression actually. There are some other models which are based on the difference, for example, between logistic functions, and I'm giving here the dates because those models are pretty old, right? So I mean, older than me even. So that's this is how the theoretician would start, right? He would take one model or the other and say let's see what's going on, and then what we would do, we would say we would, for example, apply some classical estimation technique. We would say what's the maximum likelihood estimation, for example. We would find skills which maximize the sum of logarithm of conditional probabilities of likelihood, essentially, right? And if we apply here, instead of maximization, which is based on sum of all likelihoods, if we do it via stochastic gradient, so this is kind of real-time approach. Each time the result appears, we take the gradient of this quantity multiply by some value k, I use k again like we used before, and we add it to the estimate we have to obtain a new estimate theta t plus 1, right? So, and if we write it down, actually, it turns out not to be something like that, right? Well, that's very similar to what ELO algorithm is, and it turns out that this function, which depends on this parameter kappa, I recall what kappa is. Kappa is this additional parameter we use in the modeling, right? So it has this form, right? And actually, if kappa is equal to 2, this is again the logistic function, right? So yeah, it's not that bad. So basically, ELO algorithm can be treated as stochastic gradient optimization applied to the problem of maximum likelihood estimation based on the Davidson model, right? So that's kind of interesting. It tells us that we can link the ELO algorithm to the conventional probabilistic modeling. And here I have those functions plotted, right? So this is the probability of winning at home, probability of winning away, so Z being large, so probability of winning at home goes to 1. I already mentioned that. Probability of draw is the largest when the difference between skills is 0, and it fades away as with absolute value of Z, so if amplitude of Z grows on both sides, and so on. So, okay, that's fine. What is that? Okay, so now we have the explanation, but what is the advantage here? Well, the advantage is that we have those probabilities, right? Because when we define it in the practitioner's way, remember that, sorry, I'm in the wrong direction. So, practitioner just said this. We have numerical score, we have expected score, and that's it. We don't have the probability of outcomes given the skills. Now, with what we did, we do have those probabilities, right? So you can say, okay, well, are they well defined? Does it fit the data correctly? That's a different question, but at least we now have a model which can be related to what's being done at this moment, right? Okay, so this kind of and this element. So this tells us that one of the algorithms which are being used now for the ranking, including the FIFA, they can be somehow related to the practical statistical modeling. Okay, and so this is a part which links the skills so we talked about with the outcomes, which have a different values: winning, losing, drawing, winning with some margin of victory, and so on. So I would like to go to the other part of this presentation where we talk about real-time power ranking, and again we would like I would like to mention what are the different algorithms being used. So essentially I would call the well-established algorithms, there are basically two of them, right? So one is called Glicko algorithm, also developed by someone called Glickman, so he kind of called his algorithm Glicko, why not? And it's been developed for chess, but also can be used in other contexts. The only issue, so the idea in this algorithm, as we will see, is to suppose that there is some dynamics in the skills. So the skills, so we don't have to use stochastic gradient, but we can use some more advanced methods to track the skills throughout the time. And it was developed for ternary games, so basically where we have draw, win, and away win, the home win and away win. But the model is not clearly defined over there, in fact. So it can be related to some models, but it's not as explicitly defined as in probabilistic terms. And the other algorithm is what's called TrueSkill, and it was developed by Microsoft to be used in esports, right? So this was done, I guess first, I don't remember which was actually, so essentially Microsoft is one of the developer, the company which develops the multiplayer games. So the idea of this algorithm was to rank the players, so players can be matched according to their skills. That's why it's called TrueSkill. So that the game, after the match, the online games are more interesting, and so we match the players which have similar skills, right? Okay, so those are kind of two algorithms, and my question kind of here is, what happens if the games are not ternary anymore? Can I use the Glicko algorithm? Can I use do I have to use TrueSkill's algorithm? Well, if I have to use it, I have to pay Microsoft because this algorithm is patented apparently. What happens if I have games which have more levels than 3? Right? I already mentioned that can easily happen. I gave example of volleyball where you have 6 levels and so on. So idea here is to propose the algorithm which would work with any model for the outcome of the games conditioned on the skills of the players, right? So without explicitly defining that from the very start. Right, so let's keep it generic, and this brings us to this kind of stochastic model when we have the states which evolve in time, let's say, and with each state there is one observation, right? So that's kind of general model for if those are observable variables and those are hidden variables, and we have additional assumptions, so we can call it a hidden Markov model, for example, right? So we assume that the distribution of those variables depends only on those past one step behind them, and that the distribution of outcome depends only on the hidden variables theta t. So this is this assumption, right? So that's kind of, this is first order Markov model, and this is memoryless assumption. Question is, okay, how to find the distribution of those skills given all the previous or past observations. So this is kind of classical inference problem. We use this notation _t to denote all the past to the time t, right? So this is kind of very well-known model in engineering and computer science, actually. So for example, the variation between theta t and theta t minus 1, very often it's an autoregressive model with a Gaussian innovation process which drives this model. Quite often we can have if I go back to this equation here, we have a convention. I call it conventional because it's very often used. Model when yt, the outcome, depends on the linear combination of the states with some observed xt and the Gaussian noise, right? And if this is true, theta are Gaussian, eta is Gaussian, everything is Gaussian, right? So that's the well-known case which it's used in the development of the Kalman filter, for example, right? So, and we have also the extended model. So we say, okay, yt is some nonlinear function of g of z, and we still add the Gaussian noise, right? So this is a kind of conditionally Gaussian case. So it's often used in the extended Kalman filter. But in our case, we have yt is not defined this way, right? In our case, yt is defined via distribution essentially, because yt is a discrete variable, right? It belongs to the discrete set. Those values, there is no numerical values associated with ABC, so we have this essentially the probability that yt takes value a given theta, right? So this is our case, and logarithm of this probability we denote with the letter L. So our objective is to derive the algorithm without even specifying explicitly those relationships, and we will later on be able to do that, right? So those are just to maybe root it in some well-known practice, we will refer to particular cases here. So what is A, what is epsilon, you remember? So this is what we have here. If A is identity matrix and epsilon is 0, so basically ut is always 0, theta t does not depend on time, right? So theta t is just theta. And depending on how we define the relationship between y and theta, we can have or linear regression, so basically we mean least squares model problem, or logistic regression where yt can be defined as two numerical values. L is this minus logarithm of 1 plus exponential yt, and we have logistic regression appear here. This is I close the parenthesis now, but I'm just saying that this model, when we avoid the dynamics, so basically when we say the data, the parameters are always the same, the hidden parameters are always the same, this boils down to the well-known equations, right? So just to reassure everyone. Well, what happens if theta varies with time? Well, and we have to find this distribution, right? So we have to find this. Well, with some Bayesian transformation, we see that we can relate distribution of t given the all past of t to the distribution of theta t minus 1 to the all past of t minus past and present of t minus 1, right? There is this distribution, conditional distribution of t minus 1, there's marginalization, and we still have this case here, this probability of yt given theta t. Well, then how to deal with that, right? So well, that's complicated, right? Because we don't have explicit forms for any of those distributions, right? Well, if this is Gaussian, so basically if this form is Gaussian in theta, this is Gaussian in theta, and we start with something Gaussian, everything will be Gaussian, and it becomes a Kalman filter, right? Otherwise, we have to deal with the numerical integration with m-dimensional space. Remember, we have m teams, so this theta has m dimensions. This integral in m dimension, it's not easy to be done, right? That's complicated, numerically complicated things. Or what we do, well, we take advantage of the first point and we say we will use approximations, Gaussian approximations for everything. And how does it work? Well, we suppose that this distribution is Gaussian. This is Gaussian. We take this, and this integral therefore is easy to calculate. We plug all this product, including this function we don't know, into some projection on the Gaussian distribution space, right? So this is what essentially we can do, and that becomes essentially Kalman filter. The only thing we have to somehow do this projection, right? So basically what we really need is to develop this function as a Gaussian distribution, and the details are not that important. What I'm saying here is that L of zy, as you remember, was the logarithm of this expression, right? L of zy, sorry, here. L of zy is the logarithm of this probability, which we say we will know, but for the moment it's a generic expression, and we essentially only need to know the first derivative of this expression with respect to z and the second derivative with respect to z. So that's essentially all we need to know to be able to derive the algorithm, and essentially it gives us the nonlinear Kalman filter, right? So yeah, those are the conventional equation update of the covariance matrix and so on. So I understand that derivation was kind of miraculous here, but just to reassure you, I will show an example of how it really works in well-known cases, right? Furthermore, what we can do is we can add additional constraints. We can say, okay, this is our conventional model when we use the full Gaussian distribution. We can assume that all elements we want to estimate, all elements of theta t are independent Gaussian variables. So then the covariance is essentially a diagonal matrix. we can assume that all those elements have the same variance, Vt. So this leads to this model. Or we can assume that actually we know the variance and we're just interested in the mean. This leads to this model. Right? So that's additional constraints on the Gaussian projection. And this leads to kind of simplified Kalman filters, which I call V for the vector covariance model, S for the scalar covariance model, F for the fixed covariance model. And there's one particular case, if we assume that the second derivative of which appears here is 0, we obtain basically stochastic gradient approximation. So we have kind of family of nonlinear Kalman filters which can be applied here. Okay, maybe, and it can be easily shown that in the well-known cases, so people who work in the signal processing usually assume that, as I mentioned before, that we have a Gaussian noise, so we have the assumption of the Gaussianity, and we can actually obtain the algorithms which were well known. So stochastic gradient becomes LMS algorithm, fixed Kalman fit then becomes normalized LMS, and scalar Kalman fit then becomes variable step size normalized LMS. So, but that's, I close parentheses here. Okay. So we have this kind of complicated equations, right? And how does it really work with practice? What's being done with practice? So, well, first of all, I said that those are generic algorithms. So first of all, we have to fix the model of the relating outcome to the skills, right? So first one is the Bradley-Terry model, which essentially is the same one we use in the ELO algorithm, right? So we have probability that the home team wins is a logistic function of the difference between the skills. We derive GT, which is the derivative of logarithm of that, and HT, which is the second derivative, this side minus, right? So this is one of the models. There's another model which we say, okay, instead of using logistic function, which is the CDF of the logistic distribution, we can use CDF of the normal distribution. We have all those GT calculated again, HT. So the point here is that once we define the model is defined by this equation or this equation, the rest is straightforward. We have to calculate the first derivative, second derivative. Even if they maybe appear complicated, it doesn't change the algorithm. That's the whole point. And then, why I show those two models? Well, because those two models are underlying the algorithms I already mentioned before. The TrueSkill, you remember this Microsoft, which is used in esports. And I show here this vector covariance model Kalman filter, simplified Kalman filter. And actually, if you show the equation, it turns out that they are very similar, right? So, in a way, we can make a conjecture here that this is an approximate solution of our Kalman filter, right? So what the Microsoft proposed is a particular case of what we do. And we have this Glicko algorithm, which was used in chess and esports. And this is based on the Bradley-Terry model, which is the one with the logistic regression. And again, it's essentially very similar, right? So again, we can conjecture the same. This is an approximate solution to what we showed. Okay, so of course I didn't get into the details of how those algorithms really compare, so I will show some results of numerical assessment of those algorithms, right? So first of all, I'm using the synthetic data because that's easy to manipulate, take averages and so on. It's much more difficult to make real world teams or soccer teams play multiple games against each other, because that's usually not how it works, right? So let's say we have 20 teams. Each of them play each other at time t. They play each other at times t from 1 to 1,000 and more. We generate the skills as a Gaussian, so we use this autoregressive model with some, and to avoid divergence, we have kind of dumping parameters beta here. So we know this, what is the variance and what the average of the skills is 0. After 40 days of those games, we take 5 teams out and we replace them with new 5 teams. So we have a perturbation in the system. Of course, this is not a good example for the soccer, but those things may happen, for example, in esports. You have group of players playing, and at some point some player abandoned and a new appear, and then what happens, right? How the algorithm will track the changes in the skills. We generate the result via the Thurston model, right? But and we calculate the Kullback-Leibler divergence because we know everything, so we know the distribution, we know the ground truth. So this is the whole point of using the synthetic data, right? Okay, so how does it work? We have kind of a bunch of figures here. So the first one would be to look at would be Kalman filter, which is a full-size covariance matrix, and this simplified Kalman filter, which is variance version, so basically using only diagonal one. So we can distinguish those well here, right? So this is the 40 days. Some new teams arrive, so we have a perturbation. So here there was some convergence occurring. New team arrives, so we have the tracking of the skills does not work very well, and we continue to converge again, right? This version, when all teams have the same variance, so this blue line on the initially works quite well, because actually that makes sense. All of them have roughly the same variance, but here the new teams appeared, which has variance which is definitely higher than of those which were already in place. So that's why this assumption deteriorates the convergence, right? And then you have all those others, algorithm, fixed variance and stochastic gradient, when they basically work definitely worse than those variance and matrix-based, basically, so covariance matrix-based solutions, right? Okay, so that's essentially the synthetic results, and I promised something, right? So this is what it is. So we have some results. This is the English Premier League. So I should have shown some Brazilian games, but that would be fun actually. Yeah, here we are with the English Premier League, which is, as maybe they say only, but it's one of the most competitive leagues in the world. So we have season 2009, 2010. We have a vacation here, right? 2010 and 2011. So we showed basically two algorithms. So this variance, covariance, so a vector covariance matrix, this algorithm, Kalman filter. So this is a solid line, and stochastic gradient, which is essentially kind of ELO algorithm adapted to this case. So this is the dashed line. So we can kind of appreciate that those solid lines converge slightly faster. I mean, here the skills in the dashed case at the end of the season they are practically the same, right? But we had a better idea about the skills already before. And there's one thing we should not miss, that the Kalman approach allows us to assess also the variance, or basically or standard deviation of those estimates, right? So those are these translucent corridors we are showing here. So we essentially also know how well we can trust those results, which we don't have these results in stochastic gradient naturally, right? So this is one thing. And of course, for those who know how those leagues work, so some teams, the best teams stay in the league. The worst team, I guess it was Portsmouth in this case, are removed, and the teams from the teams from the second tier, which is Championship League, are promoted to enter the games, right? So for this next season, we have Blackpool, which was not before in the previous season in the EPL, right? So it starts from zero and it starts converging here. And somehow similar results can be applied in different sports, of course. So here yeah, you can understand why I'm using hockey here, because hockey is the most fascinating sport, of course, for Canadians. And we have somehow similar results, but not exactly the same. We can see that the convergence is pretty much slower, right? And somehow through the seasons, from one season to another, we can recover the previous results and follow up. And it works relatively much better than starting from zero. Here we don't have promotion system and anything like that. So why this convergence is much slower? Essentially, those teams are very well, the league is well balanced. So there is a principle, those are American sport, North American sports. They have the principle of salary cap, so you cannot have extremely good teams because nobody would be able to pay for those players, and usually when you have too many good players, they have to be traded off to other teams. So the budget for the players stays the same. So it's and this means that essentially the differences between the skills of the quality of the teams is not as large as it is in the EPL, when such conditions do not exist simply, right? We can spend as much of the players as we want. I mean, as far as I know, maybe some constraints on that as well. All right, so yeah, so that brings me to the end, and good, we finished before 8 o'clock. I was not rushing through, I hope, and yeah, so essentially my idea was to kind of give you the overview of what the ranking is about, right? So, and kind of theoretical or maybe practical or maybe both conclusion is that actually those algorithms which are developed by practitioners, I call them practitioners because often they are developed without any formal statistical framework. They can be mapped to some ordinal models or some or skills dynamic models as we showed, right? So that's a good part because essentially it gives us a way to also find the parameters of those models in more structured way, right, without guessing. Well, I focused a bit of time on this Markovian model and Bayesian inference, showing that it leads to generic real-time ranking algorithm. And so those actually kind of come out from that, right? So those algorithms which are used, which are very well known, ELO, Glicko, TrueSkill, are particular cases or approximately particular cases of our rating or ranking algorithms. Yeah? Well, I show you some results based on synthetic and empirical data. Well, I used EPL and NHL, but we also applied it to the American football. It can be applied. We have currently running it for the FIFA, international FIFA and international volleyball as well. So yeah, it can be applied actually in any case when it's properly defined model. All right, so here we are. Thank you very much for, I hope, your attention online. And well, of course, we still have time for some questions. I promised to finish before 8, and here we are. Thank you, Marcio.
Thank you, Professor. We have 2 questions. The first one is Enzo. Is there a way to estimate the optimal value of the learning age, or do you have to check the behavior of the data for different values?
Yeah, so I don't have it, and that's a good question. Yeah, so it's essentially in the context of adaptive filtering. Yeah, that problem is not really solved, right? There are some methods to. Okay, so this is in adaptive filtering of signal process. In machine learning, the learning creators, so those are essentially the hyperparameters, right, of the algorithm. And There are some works on that. I'm not sure how well they apply throughout different cases. And yeah, so the easiest answer, I don't have it. Would be great to have it, right? But would be. What can I say though? That it's the Kalman approach is somehow it allows us to, if we go back to what we showed, we don't have essentially the let's put it this here, right? So we don't have the step, right? The step is adapting itself to the variances, right? So those are the means, so those are the skills. There is some adaptation of the step throughout this variance. So yeah, there are algorithms which allow us to somehow estimate variances from the previous estimates. Those are heuristic though, and in that sense, yes. But if it's stochastic gradient, I'm not that sure. It could be done. Yeah. But I haven't been doing this kind of work. Yeah. Very good question. Thank you, Enzo.
Okay, we have another question. Richard have two questions. The first one is it possible to compare those methods? I mean, in terms of accuracy, because to my understanding, the rank value itself is sort of subjective, right? It feels like too many variables.
Yeah. So, yeah, very good question, Richard. So thanks. So yeah. So the problem with practitioner, what I call practitioner perspective, is that you cannot do it actually, right? So everything, you have just a rank. For example, let's take a look at the FIFA ranking, international FIFA ranking, right? So you have some team being better than the other. Belgium was number one for a long time, and everyone was scratching their head. Why it was Belgium, right? I mean, so we have nothing against Belgium, but it's somehow people were the only reference we had to assess those ranking algorithms was our own intuition. But the whole point of using the ranking algorithm is to avoid intuition, right? To have some objective metric and to assess everything in objective terms. So, yes, our intuition is subjective. The practitioner perspective to approach to that, if developed without a model, is also subjective, right? Because we have those expected score, which is subjectively defined. But if you take practitioner perspective, you start with the model, right? If you start with the model, you can assess how well you predict the data, right? So essentially, prediction is out of sample evaluation, right? We assess and we can calculate logarithmic score and all those measures, and essentially, this is what I showed actually here, right? This is the objective evaluation, because I'm showing the Kullback-Leibler divergence. Of course, this Kullback-Leibler divergence can be done only if calculated only if we know the ground truth, right? So we know what is the actual probability of the game and what is the prediction of this probability of the game result. But even in real world, we can assess how well one algorithm works and how the other works. So we did a work on the FIFA ranking, right? And we can show that, well, we can improve this logarithmic score, which is kind of machine learning metric to use the prediction. And we also improve the accuracy of the prediction, right? So by using better models, we can improve the prediction by a couple of %, which is not negligible actually in this context. So yes, accuracy can be one of the metrics. It's maybe not the best one, right? But there are different metrics which can be used. Depends what we want to do. And then it is objective, right? In the terms of the well-defined metrics, right? And the last part, if I understand, it's too many variables in the parameter, or are we referring to that? Maybe you can clarify it, Richard. I'm not sure if you are referring to the parameters of the algorithm, or are you referring to the skills of the teams as such? So if you clarify that, I will be able to answer.
Okay. Yeah. It's too many variables in the skills.
Yeah, so that's the essence of the ranking, right? So we have here one or maybe two parameters per team. So of course we need enough observation, if I understand your comment in this way. So of course we need sufficient number of observations to be able to infer those parameters, right? So yeah, so that's maybe a tricky part if we talk about ranking in the professional leagues, which has one season, let's say, right? And let's say EPL, English Premier League, for example, they 20 teams, so they play round robin with each one, so there's 19 games times 2, right? 38, something like that. No. How many is that? 19, right? So they play 19 games, right? Each of them. Is that correct? Yeah. So it's a very limited number of games, right? Number of observations per team. That's why the convergence may be complicated and so on. For example, if you look at the hockey, ice hockey games, there's much more, right? So each team plays 80 games in one season. So that you have much more observations. Convergence was slower though, because for other set of reasons. But and maybe also this will explain why those power ranking algorithms are mostly used in those international competitions, because they don't have end, right? There's the soccer games internationally. There's no end of the season, right? Everyone is playing all the time. I mean, there are some restriction because international competition, or they don't want to get into conflict with some other events, but essentially this is where those rankings are being deployed. And yeah, so we have those FIFA, we have Volleyball Federation, which started 2 years ago, this dynamic ranking system, which is also based on the kind of approximate stochastic gradient solution of the maximum likelihood estimation. Yeah. So too many variables for some cases, yes, but the same issue appears. Whatever ranking you want to do, you have the same number of observations, right? So the question is how to find them appropriate model. Okay, thanks, Richard. Yeah.
Richard has another question. In online games, people complain a lot on how unbalanced some matches are, especially a team-based game with individual player scores. Is it a good idea to try to make everyone have around 50% win rate?
So, well, I cannot talk to what is the strategy, but from what when I was mostly reading about, I'm not a player, right, in the online esports, but yeah, I can understand why it's an issue, right? Because you want it to be interesting. The game has to be interesting for everyone. Right? If you know you lose, there's no interest. If you know you win, there is no interest, right? So it has to be you have to have high entropy of those events. So and from what I hear, yeah, those ranking were used to match people so that the uncertainty was maximal, right? So the 50% was around that, but yeah, it's always a little bit on and off, and it always depends on who is available to play, right? Because that's not a pre-scheduled concept, right? You have people connect, and you have immediately to match them, and sometimes you don't even know, you don't have an estimate of the skills because they may be new players, right? So yeah, that's a difficult problem. Yeah.
And the last question, Guilherme, is it possible to use neural networks to solve these problems?
Of course. Neural networks solve everything. No. Actually, I don't think so. Right? So, I mean, if it's a real-time ranking, I really doubt it, because it's as previous question pointed out to this issue, that you have really very few observations, right? It's possible probably that those neural networks can be used to extract some interesting parameters, right, of the game, because now we are talking only about outcomes, right? But you can talk about some other aspects, right? For example, what happens if you start considering not only the outcome of the game, but some other observations, like in soccer, number of corners, number of free kicks, number of fouls, right, and so on, and from that you want to extract information about ranking, right? You first of all would like to know maybe which parameters are important and so on. But yeah, so that I'm kind of speculating now. For sure, people will try to use neural networks, but here I think the problem is that we have very few observations usually, and we have to do it online. Yeah, so yeah, it's kind of old-fashioned is maybe the best way to do. And actually, there is another problem, and I went over this issue. This practitioner perspective and theoretician perspective have also different motivations, right? Practitioner, I mentioned this positive feedback, and people intuitively understand, what this algorithm does, right? They say, okay, if I have more points than expected, I should be better, I should have I should gain in skills. If I underperform, I should lose skill points, right? So you can explain it in a way, and people kind of accept this because it has an intuitive kind of meaning to them, right? So, and you wanted those algorithms also to be relatively simple, right? And transparent. Most importantly, they have to be transparent, because the stakes are high here, right? This FIFA ranking algorithm, for example, is used to select which national teams will participate even in the knockout competitions, right? So if you don't have, it doesn't matter that much here in South America, but in Asian and European competitions, there's a lot of teams, right? So first of all, they have to have enough points even to enter the qualification tournament. So that's important, and it cannot be done on some abstract and wrong, kind of not transparent way, because everyone has to be able to repeat those calculations. And if you do neural networks, I don't know how would that work, right? So, and how would people be, if everyone would be happy about it? And I can comment on that a bit more, but if there are any other questions, so.
Yes, now it's the last question. Guilherme, could this mathematical modeling be useful for sports scheduling, determining dates and home away matches based in the win-loss expectations in order to balance the tournament?
Yeah, it could be. Yeah, it could be, but the there is always this, so this kind of similar to this esports, right? You want to have a competition, but the stakes are not the same. Right? The stakes are quite different, because can you imagine that Brazil, for some calculation or mathematical reason, is expelled from the qualification for the FIFA World Cup? That would be a revolution, right? People would say, okay, this is the conspiracy against Brazil and so on. No, you want to avoid those controversies, I think. So, yeah, although it affects the result. Okay, so this is about the FIFA tournament. Now, if we talk about balanced tournament for design, yeah, that's again a difficult one, right? Because you want to give everyone a chance and so on, but of course you have to expel some teams or not let some teams to participate. So I don't have any clear example, I think, now. Oh, actually, yeah, I do. If you look at the tennis, you have to have some points to actually enter some of the tournaments. So and it's quite often actually the case, right? So you have to be sufficiently well ranked on this international ranking to even participate in some tournaments. So it's the whole idea is to, of course, to have players of the good level. So I'm not sure I'm really answering exactly the question, or the kind of pointing that it's already being done, and the whole idea of this kind of work is to have a better understanding actually what is the meaning behind those ratings, right? By providing the models, we have a better understanding what those rating algorithms do. Yeah.
So, thanks a lot. I have my last question. Can I use these methods to ranking the students?
Actually, it is. The ranking of students. Yeah, it's used everywhere. It's everywhere where you have to have some where you need to make a decision, right? Because it's kind of decision aiding tool, right? So if you give stars to the Uber driver, I don't know if there is Uber in Brazil. Yeah, there is. So this is basically your ranking the service provided to you, right? If it's about restaurants or so, it's used a lot, right? If you do research on the Google, there is an algorithm, ranking algorithm for the pages, right? So it's called Google Rank algorithm, and so it works like a different way. It's based on some Markovian assumptions as well, but yeah. So of course it's used, and it's used also to rank students. Actually, it's one of the very first applications, I mean, kind of which were to assess how well students perform for some task, and at the same time the same tasks, the difficulty of the task was evaluated, and it's kind of ongoing work. There's a lot of work on that as well, in educational context, right? Because it's used a lot in social sciences in general, because you want to assess different elements, what's better, what's worse, and you want to do it in an objective manner, right? So I gave examples in sports because those are more fun, but it's quite a large area actually, yes.
Okay, we coming to the end of the talk. Thanks, Professor Leszek. It's very interesting and a nice talking. Thank you very much.
Thank you, Marcio, and thank you everyone for your interesting questions and bearing with me for 1 hour. Thanks a lot.
Ok. A gente vai encerrar então. I will switch to português. Nós vamos encerrar então. Obrigado a presença de todos e até semana que vem.